this next year is going to be really exciting, I think, for the air quality team. Probably the atmospheric dynamics team is going to echo that, with the Courage project starting up in December and going for a year. We're really hoping that the measurements we've started taking, that Ben will be describing soon, will help us lead into that Courage campaign more prepared. Obviously, we want to be able to do more, but we're limited by people's time and ability to analyze the data that we have. And so I think, just to give you an overview, we have currently right now some fixed site measurements going on, briefly halted for some of the instruments due to some power issues and instruments being down. Just about a mile from Hopkins Homewood campus, looking at concentrations of particulate matter and the composition of particulate matter. We've got some greenhouse gas measurements there as well, and some trace gas measurements, ozone, NO, NO2. The mobile lab has been out and about. We visited a high school science school this summer and kind of let students see what we were doing with the mobile lab and made some measurements in support of other projects. And so we're starting to build the data set, I think, that's really going to help us think more about what we can do in Courage and build that basis for that. So with that, I'm going to turn it over to Ben Nault to show some of the actual data that we've been collecting with the instruments we have running at the BSEC site.
Cool. Actual slide shows up, right? Cool. So I wanted to give a quick update on both our stationary and mobile AQ measurements and kind of what we've seen so far this summer, which is helping kind of help with the questions that we want to ask with the data, as well as some of the projects that the graduate students want to work on. And yes, those are my two official titles. Pete will agree with the second one. So for the stationary site that Pete was talking about, that's about a half mile to mile from Johns Hopkins right now. I've already shown this figure, but there's updates on how long we've been collecting the data and which instruments have been unfortunately down. So the SMPS, or Scanning Mobility Particle Sizer, we've been running it for about 5 to 6 months now. I need to start working on processing the data for people to access it. The ethylometer, which measures black carbon, and you can also get brown carbon through it, has also been running for about the same amount of time, but we've been loaning this from our group, and we will be getting a new one through BSEC soon that we'll be adding. So it'll be the same type of measurements, but shiny and new, so that'll be exciting. The time of flight aerosol chemical speciation monitor with extended resolution, or you can call it the ACSM-X for short, which gives us aerosol concentration, composition, and information about organic aerosol, including where it's coming from, was running for about 4 months. During a storm, we had a power glitch, which led to us not being able to run it, and we had to send it back to Switzerland for repairs. It just came back, and now I'm working on trying to get it running again and making sure the data makes sense. Ozone has been running off and on for about 3 months. It's another instrument that we've been loaning from our group, but we'll be getting a new one through BSEC, as well as a new nitric oxide and nitrogen dioxide instrument. So that will give us a nice suite of the photochemistry and trace gases. Our methane, carbon monoxide, and carbon dioxide Picar was running for about 4 months, and the same time that the ACSM-X went down, the methane, carbon monoxide, carbon dioxide Picar went down, and that's been sent back to Picar in California, and waiting to hear what repairs are being done with that. And then the other instruments that we're planning on installing in the next month or 3 is a methane ethane Picaro, and I'll show why we want the methane and ethane to start understanding sources of the methane that we're seeing. A unit mass proton transfer reaction mass spectrometer, which will give us information about biological volatile organic compounds, oxygenated volatile organic compounds, and aromatics. And we started some discussions with potential guest groups to start adding instruments for short or long-term measurements at our stationary site. So what does some of this data look like? And I'm wanting to show this. I'm starting to work on how to get the data uploaded, which will be one of the slides towards the end. So here's a time series of all the aerosol composition and mass concentration that we've measured with the TOF ACSM-X before it went down with repairs. Pink is chloride, orange is sulfate, red is sulfate, orange is ammonium, blue is nitrate, and green is organic aerosol. And we've been measuring from mid-March, about when spring started, till mid-July or so. And what you're seeing is at the beginning of spring, and as we're getting later in spring, the inorganics were really dominating, especially the nitrate. And there's also some time periods where the nitrate was high, which might be related to cooler temperatures and relative humidity, or potentially some biomass burning that we're seeing once in a while. So we need to look into why we were seeing high nitrate later in spring. But as
Ben,
yeah.
sorry to interrupt, but can you just confirm that these plots are showing kind of the sum? So the organic is just the area of green that's showing?
Correct.
Okay.
Yeah.
Oh.
I'm trying to give updates for people who may not be familiar as much with the instruments in the chat, for those of you who are following along. And apologies, I can't keep up. There's a lot of information here. So do what Darren just did and jump in if anything isn't clear. We're happy to clarify.
And then as we get later in the season, as photochemistry starts kicking up and the emissions change, we're seeing that the organic aerosol, which is the green, is increasing a lot. So trying to really start to disentangle how these different compositions are changing across the season and what that means for sources and physiochemical properties, as well as what people are being exposed to in Baltimore, is an important question that we're starting to look into. So if we look at this as a monthly average, so what's plotted here is in the black line is the PM 2.5 that's being measured at the Essex EPA reference monitoring site. And then the monthly average organic aerosol in green, nitrate in blue, sulfate in red, ammonium in orange, and chloride in pink, as well as our black carbon in black, adding up to the sum at our BSEC site. So note that this is like a 10-15 mile difference between the two measurements, but where we were measuring at the same time as the Essex site, there's fairly good agreement between the two sites, which is providing confidence on our measurements and the general question that we've been trying to understand of why PM 2.5 is generally constant across Baltimore. We think it's because the sources are pretty low in Baltimore. It's mainly photochemistry, but BSEC will give us more information trying to disentangle and understand that. But this is further showing that, again, the nitrate is decreasing from the cooler, wetter seasons to the warmer seasons. And this is because nitrate likes cool weather and wet weather to stay in the aerosol phase. As soon as it starts getting hot and or dry, the nitrate will leave the aerosol phase and become nitric acid. And then we're seeing that the organic aerosol is increasing as we get into the warmer seasons. And that's mainly because of the production of secondary organic aerosol that I'm showing here in green. So as photochemistry increases, we're producing more secondary organic aerosol from biological volatile organic compounds and other volatile organic compounds undergoing photochemistry and partitioning into the aerosol phase, while the primary organic aerosol is staying about constant across these time periods. So that's our quick, real story about aerosol before I move to gases. Yes, Pete?
I just wanted to add one interesting thing. Can you go back one slide? So the black carbon actually goes up and then levels off. We usually associate black carbon with traffic, but we've had a lot more wildfire influence in the last few years. And if you go to the next slide, the primary organic aerosol, which we also associate with direct emissions from vehicles, is actually going down. And so that means that increase in black carbon is probably likely due to an increased fraction of the particulate matter being due to wildfires. Even if we don't have a massive wildfire event, I think we've been seeing a lot more trace wildfire smoke making up some of that particulate matter as we transition into the warmer summer months when the wildfires tend to be happening farther west of us. So that is actually a significant source. And I think that's going to be something interesting that we're going to have to grapple with looking forward with climate change.
Thanks for pointing that out, Pete. I forgot to mention that.
Ben, one other question, if you can go back to the other slide. Just curious, like from that EPA reference monitor, what does that mean when the aerosols exceed that concentration, if that has any implications from the EPA, such as if concentrations exceed some threshold for a given amount of time?
So right now, what is the 24-hour average value? Is that 35 micrograms, Pete?
Still 35, yeah.
Yeah, so right now, at both a daily average and annual average, Baltimore is not exceeding the 35 micrograms per meter cubed for the daily exceedance and 9 micrograms per meter cubed and the yearly exceedance. We are extremely close to the 9 micrograms per meter cubed on an annual average, though. We're typically somewhere between 7 to 8.5 micrograms on an annual average each year, and that value hasn't really been changing for the last decade, which indicates that we've tampered down the primary emissions really well, but now the secondary sources are becoming the dominant story, and trying to disentangle how much of local emissions that are contributing to the secondary sources versus stuff that's being transported into Baltimore from upwind locations. So we have a bunch of forested areas upwind from us and the coal power plants and all these other sources. So how much of that is leading to us staying at the 8 to 9 micrograms? And what does that mean in the future when EPA brings down the reference even more? But right now, the black line is the measurement. It's not saying that this is exceeding values. It's what is actually being measured at an EPA site.
Oh, thank you.
Yep.
Sorry.
Okay. So to change tracks to gas phase measurements, just to highlight everything we're looking at. So I've plotted here on the left is the diurnal pattern of the methane that we've been able to measure for 4 months at the BSEC site. And on the right, I'm just showing an example zoomed in time series of the methane to highlight the similarities and differences that we're seeing depending on how you're looking at it. So with the diurnal plot, we're seeing that the methane is kind of increasing until the planetary boundary layer starts growing in size and starts leading to enough to make sure that the methane mixing ratio decreases. So what's interesting is this increase during the morning, nighttime and morning, showing that both because the planetary boundary layer is low and the amount of methane links that might be around Baltimore, this is leading to an increase of methane overnight until the planetary boundary layer grows to enough depth that mixes and causes the mixing ratio to go down. And that's further highlighted when we look at the time series here, where the different times I'm showing are the times that we're seeing these different spikes in methane, to indicate that it's not something that is always occurring at the same time, but we're getting these periodic spikes of methane throughout the day that we're sampling at the current stationary site. So really trying to understand where these emissions are and what that means for an urban, for Baltimore's emissions of methane, are some things that Pete, Scott Miller, and I are interested in. And then just to highlight NOx measurements that we're doing currently with our instrument that's on the mobile van that I'll be showing in the next couple slides. When the mobile van isn't driving around sampling, we're still sampling with some of the instruments at the garage at the same spot as the other instruments. And we're seeing the typical diurnal pattern of NOx that rush hour between 4 to 8 or 9 a.m. and after 5 and 6 p.m. increases of NOx in the area, but it's starting to get to a low enough mixing ratio that might indicate different type of chemistry that's happening that we're looking into. Yes, Pete?
This is NOx, NO plus NO2?
Yes.
Okay, so just to clarify for people, we often talk about just NO2, but this is actually the sum of NO and NO2, which interconvert rapidly during high sunlight periods.
Oh, hi. And this is Kelly Cross. Sorry, I'm just joining in, and I'm a little late. But what does NOx mean? What is NOx?
NOx is nitric oxide plus nitrogen dioxide.
I just
So
put
it's
it
the
in-
sum of the two because they interconvert very quickly.
So,
So real,
the EPA only measures NO2, is that correct?
They measure both, but
yeah,
the only criteria pollutant so that it has standards behind it is NO2.
But so when you're looking at the standards, it's not the NOx, they just worry about the NO2 that they've measured.
We have both. I mean, we have
Yeah.
the sum because the sum
I
from a
just don't,
perspective
I-
is better.
yeah, I didn't plot NO2 here because this was stuff that was doing very quickly,
Yeah,
but
okay.
we have NO2. So real quickly about Pete's mobile laboratory that he's fondly called Mom and Pop, and he is very proud of the acronym, meaning Mobile Observatory Measuring Particles and Other Pollutants. And look at that nice grin that he has on his face every time it comes up. He's very proud of that. Think of an Amazon delivery van. So it's a very large van, which is why we're able to fit all these instruments on here. And we also have a gas powered generator. So we're able to measure for long periods of time while driving, since we don't have to worry about battery backup. So we're able to operate many mass spectrometers and other types of instruments to look at particle phase measurements and gas phase measurements to really look at the whole picture of exposure and photochemistry for an environment. So I'm going to show a couple figures of different gases that we've measured in our various drives that we've done this summer across Baltimore. So first is NO2, just to confuse you, but to make Darren happy. So NO2 is part of the total NOx, again, NO2 plus NO. NO2 is an EPA criteria as well as something that is directly measured by satellite. So looking at what NO2 looks like across an urban environment is good both from a criteria perspective, but also to start doing intercomparisons with satellite. So this is from 3 different drives that we've done in Baltimore. I need to process the other drives that we've done just so I can start adding it on here. But you can start seeing that there are hot spots of NO2 that I've colored here between 0 to 20 parts per billion by volume, that when we're on very busy roadways or near busy roadways, that we're seeing much higher NO2 than the neighborhoods that aren't as impacted by busy traffic. We also have a formaldehyde measurement that, unfortunately, it's another instrument that's had to go back for repairs, but we're also seeing very contrasting and interesting differences in the formaldehyde across urban environments. Formaldehyde can both be primarily emitted as well as produced through chemistry of different volatile organic compounds. So we have to try to disentangle and understand its different sources within an urban environment, because it might be coming from inefficient methane sources such as boilers or things like that, as well as photochemistry. And what we're seeing is very high amounts of methane in some neighborhoods and long roadways. So we're really trying to understand, where is this formaldehyde coming from and how is that impacting the communities of Baltimore? And then finally, here's methane that we are also looking at, and going back to trying to understand, are there methane leaks? What are the magnitudes and sources of the methane leaks? So we're seeing in certain neighborhoods that the methane mixing ratio is really lighting up higher than the typical background that we're seeing across Baltimore. So really starting to pinpoint and understand where these methane leaks are and what is the leak amount and how does that contribute to the overall methane footprint across Baltimore. So some of the projects that are potentially being pursued by 2 of the students in our group, one by Ariana, is she's interested in looking at PM 2.5 and how community groups understand PM 2.5 versus what is actually in the PM 2.5 and how that impacts their health, and what are some mitigation steps that the community groups can do to reduce their overall exposure. And then Lalitha is interested in looking at how NOx controls PM 2.5 mass concentration and composition, especially when we're having high nitrate in Baltimore. And some of the things that I'm currently have on my board is getting the X and Picaro back online for measurements, working on workflows so that we can start posting data and more quickly processing data, and working on multiple grants for funding more drives with the mobile laboratory across Baltimore. With that, I'll take any questions.
I have a question. When you were showing where those the NO2 high concentrations were, and even the methane, do you have any sense of how far away from the roadways those you know, I guess the mobile van is just driving on the roadways to measure that stuff. Is there any sense of how diffuse that gets the further you away you are from one of the roadways?
That is one of the questions we're interested in trying to look into, and there will be a couple different ways that we can look into that. We have a methane Picaro backpack, which if we see these hot spots, we can stop and start trying to follow the methane sample until we get to it if it's an area that's easily walkable. But you can also try to create driving routes that you can try to drive towards the source as much as possible. Yes, Pete?
And Kelly, I think we want to chat with you too. There's some potential funding through a pilot program where we can maybe get money to do more in-depth measurements in key neighborhoods, and we need letters from community groups to do that. So for community folks on the call, I see Doris, Dr. Doris, you're on the call too. We may want to chat with you about potentially doing, instead of larger surveys, more focused neighborhood style measurements to get a better idea of what's in there. And so we can certainly be in touch with you about getting letters of support and trying to work out a way to answer that question you had, Kelly, about NO2.
Thank you. We want to acknowledge that we did receive a visit from the mobile van in the Broadway East community. Very empowering for the adults and the students. So thanks again.
Thank
You're
you,
very
Dr. Doris.
We enjoyed it. I see 3 hands. I'm going to just go in the order that they're on my screen. So the other Benjamin.
Thanks. I just wanted to kind of re-advertise. There's a graduate student here named Helen Kenyon who's not on the BSEC project, but she's working on methane fluxes in the northeastern corridor, so Baltimore, DC. And she's seen some kind of interesting patterns in the methane flux of Baltimore. And I mostly just wanted to say that again to make sure that, you know, hopefully there's a lot of cross interest, and she's been communicating with the BG&E folks to try to understand why there's patterns that she's seeing, and some of the spatial data that you have might be informative to her and vice versa. So that's my.
Okay, thanks, Benjamin. Go on.
Yes, well, very great work. I just want to check one thing. When you compare PM2.5 concentration and their speciation with the EPA PM2.5 concentration, that the black solid line is a little bit higher than your measurement. So I think the ASIS measurement side, their measurement method is a little bit different from the other EPA. That is 1 in 3 days collection method. So
No, this isn't from the filters. This is from the actual online monitoring site. So it's not the 1 in 3 days.
so that one is the beta ray method. Okay.
Yeah.
All right. So do you have did you use the same way? This in your side you also measure the PM2.5, so your method is the same as EPA.
No, the EPA continuous PM2.5 is just measuring total PM2.5 continuously. Ours is the composition of PM2.5 that we're adding up. So if our composition adds up to the total PM2.5, there's closure. If it doesn't add up, there could be some missing components such as like sea salt or soil.
Sure. Okay, thank you.
Larry.
Yeah, thanks for a really interesting overview. Do you have plans to be, this is related to the question of distance from the roadway. Do you have or do you plan to acquire meteorological information, wind direction and speed, atmospheric stability? And I think you mentioned you have the ability to differentiate between primary and secondary. pollutants. It might have been what Pete wrote as arm wavy. But if we could look at the distribution of plumes coming from mobile sources, in other words, the major roadways, is that something that you're looking into or planning on looking into?
So on our mobile laboratory, we have a GPS meteorological probe that gives us wind speed and wind direction. So that's one way. Our stationary sites has 2 or 3 different ways of measuring wind speed and wind direction. And we can use, for example, the methane ethane backpack that allows us to differentiate if the methane is coming from natural gas leak versus more microbial activity that's either wastewater or landfills or other things. So we have a couple ways to try to differentiate that. Is there anything else you want to add, Pete?
Yeah, I was thinking more of the NOx and PM coming out of tailpipes of mobile sources, and this would be a link to the traffic component of the study, which I'm not sure how far we've gotten to. Can we estimate what the traffic volume and fleet type is in the major arterial roads?
That Pete and I have not thought about trying to do that. I feel like that's something that we would have to try to pull in like MDE and Maryland Transportation to help with that. And I'm not sure if our sites and the drives that we do would really help with that, with how we're not doing systematic multiple drives. So it'd be really hard to do something about traffic.
Yeah, I think we just identified traffic as a gap in the whole project. I don't know if Ben is on, if he could comment on where we are with the traffic component.
It depends on, I guess, what you mean by traffic. Car emissions are going to be very variable depending on vehicle speed, stop and go, and
When they started.
And then the
That's right.
concentrations that we measure are going to be reflective of also of the boundary layer height and whether or not the boundary layer is broken up. And so I think we will have ways to estimate traffic impact. Certainly for particulate matter, we can say how much of the particulate matter is likely coming from traffic compared to the other components. But if you're looking for traffic counts, I mean, I think we will need some kind of work with the traffic folks to do that type of work. But yeah, I mean, it's a question of what comes out of the tailpipe versus what we breathe, time of day, traffic style, and all sorts of things. We're relatively close to I-83 as well, in Baltimore. And so they're, you know, that's an interstate that actually kind of flows better than most. I mean, DC is an interstate that doesn't flow. And so I think there's a lot of things that are that we just have to think about, but we do have ways of seeing how much traffic is influencing these different things, whether or not we can identify specific unit emissions, basically.
Yeah. Mm-hmm.
Yeah, and Larry, just to jump in, I can confirm that we are not currently doing that through the transportation theme either. But our transportation team has a lot of interesting social data about traffic, and then we might be able to integrate that with a transportation center that is here at Hopkins. So I'm glad you raised it because it could be a good area for cross-team collaboration going forward.
Mm-hmm.
Darren?
No, I took my hand down in the sake of time. I can annoy you some other time with questions.
I think we've gone over time, so it's atmospheric dynamics turn in the hot seat.
Yeah, thanks. And I think the order was going to be Ben and then Jason. That still sounds good.
So just to lump in, to lead in some of what Pete said, we weren't exactly sure of the structure, so we've just decided to find that two people are going to give short talks on stuff they're doing, and so I think it was Ben first.
Yeah, I'll go first.
Yeah.
Let me share screen here. Can you guys see this? Great. Okay. So I'm Ben. I'm an assistant research professor at Penn State, and I'm going to talk about turfgrass fluxes in Baltimore. And for the sake of time, I'm going to just ask for, let's just hold questions until me and Jason are done talking, except if you're one of the steering committee members. You guys can ask questions whenever you want. Okay, so you might have heard that we put up a turfgrass flux tower in Baltimore. Why did we do that? Why do we care? Okay, here I'm showing two maps. Let's start on the left. This is an estimate of where turfgrass might exist in the United States, and you can see it's more or less concentrated around urban areas. And here's a map that Jason made of the Baltimore area where we estimate turfgrass to be. And the point of these two maps is that there's a lot of turfgrass out there, and it's concentrated in urban areas. This is a urban vegetation type in the Baltimore area. According to the Chesapeake Bay Land Cover Database, there's more turfgrass than there is trees in Baltimore. So if you're looking to model vegetation fluxes in the city, you have to do turfgrass. So that's why we're doing this. What are we doing? Okay, we put up a flux tower which measures fluxes of carbon and energy. I have a little video of me and Nick setting it up. I'll play that while I'm talking. And here's where we are. Here on the right is a map of Baltimore, Inner Harbor down there, the study of Johns Hopkins, etc. Clifton Park is over here in the top right-hand corner. I hope you can see my mouse. I've circled the field, the old Clifton Park High School campus, where the site is set up. And this will also be the site of the Courage campaign, by the way, the very same field that we are measuring the turfgrass fluxes in. In my little inset map here is a zoomed in version of where the flux tower is, this little pink dot. This is a climatology of where we think the fluxes that we're measuring are coming from. And basically the point of this is to say that most of the fluxes that we are measuring are coming from within the field that the tower is sitting on top of. So we're measuring grass fluxes, and hopefully only grass fluxes. What do we see in terms of our turbulent energy and carbon fluxes? So there's a lot of data here. I'm going to start kind of slow and work my way through. Okay, so we're looking at when we started measuring the tower in mid-April up till the end of August. I haven't processed the data for September yet. On the top panel, we have carbon flux, which is actually CO2 flux. We're not measuring methane, so that's actually not exactly correct. We have on the second panel sensible heat flux, which is basically the movement of hot air. And below that is latent heat flux, which is an energy flux associated with evaporative water. So if you evaporate water, there's some amount of energy associated with that. This is that energy associated with that water. And then on the bottom, it's just air temperature. And so what I want to point out here, and I should also say, in this case, we're using the meteorological convention where negative means that it's going into the ground and positive means it's going into the air. So looking at the carbon flux here, we can see that we have a lot of negative carbon fluxes in the early part of the year, right after we started measuring. And then it really kind of shut down somewhere around mid-June, where we have very few positive carbon fluxes, very few positive carbon fluxes as well, which is kind of interesting. And then pretty much at the end of August, we start to see more growing fluxes again. The energy fluxes follow a similar pattern, but kind of opposite, where latent heat flux, which is the water flux, that's the one that's associated with the movement of water, but it's also the turfgrass facilitates that water movement. And so if the turfgrass is not growing, there's not going to be as much latent heat flux, and that's what we see here. So in the midsummer, latent heat flux is kind of suppressed, and therefore sensible heat flux increases. And this is all happening during the really, there's some like major heat waves, but it's just been a generally hot summer in Baltimore, so it seems. Okay, so we can divide this time series up into three major parts that I'm calling growing 1, which is the early part of the year, dormant 1, which is this mid part of the year, and growing 2, which is up till now, basically. If we do that, what I'm going to do is look at these on a diurnal time scale. So this is what an average day looks like for each of those individual seasons. This is carbon fluxes. And what I want to point out is, negative fluxes, we see a lot of growth, but we also see positive fluxes at nighttime. This is respiration through soil respiration or plant respiration. And see growing 1 and growing 2, I think, are fairly similar. They have actually growing 2 seems to be doing a little bit better, even though air temperature has not gone down quite as much. Oh, let me go back. Clearly, there's not a lot of growing happening during the dormant season where the negative fluxes are almost zero. But I also want to point out that the positive nighttime fluxes are suppressed as well. That's kind of interesting because it's not just growth that's being suppressed, it's also respiration. We know the temperatures are high. Average temperature was almost 31 degrees Celsius. And so basically this effectively means that it should be unlimited in terms of temperature. So it's probably water limited. This field, it gets very dry. I know Kathy actually went out there to measure soil moisture during this period, and the soil, it was too stinking hot and too stinking dry to even get the soil probes into the ground. But it would be cool to have some soil moisture measurements out here. Okay, now I'm going to switch to turbulent energy fluxes, where we're looking at the same 3 periods, and basically the same kind of idea, where we just see a real suppression of the latent heat flux during the dormant season, and then a return to latent heat flux during the second growing season, and that energy gets shifted into sensible heat flux during the dormant season. And we don't really see a change in the nighttime sensible heat flux, so the nighttime temperature inversion is still present. And just to reiterate, the reason this is important, other Ben mentioned how the boundary layer grows and shrinks. Part of our effort here is to model weather in the boundary layer in the Baltimore area. I've already shown turfgrass is a large part of the Baltimore urban area. The way the boundary layer grows and shrinks is entirely determined by what these fluxes do, what's the distribution of latent and sensible heat fluxes. And from what we've done for our preliminary work, Jason's going to talk more about this in a second. Turfgrass almost does not exist inside the weather models as they stand. And so we're probably not getting the boundary layer right either, would be my guess. So that's basically what we're going to be moving on to next. We're going to be putting out more flux towers, which are not just turfgrass. It's going to be a mixture. We're going to do the Broadway East Tower and the Howard Park Tower. We're going to do some model comparisons, Wharf, Elm, VPRM, etc. There's going to be more measurements, courage. We can also turn this site a little bit into a turfgrass lab if we want to add in some more soil moisture sensors or some weather sensors. I know Darren had some plans to put something nearby, and I know they biked by just recently. And that's it. So Jason has time, and then we'll take questions at the end of both of us.
Yeah, okay. I'll just jump right into it then. Because it is kind of playing off a very similar thing, but a little bit different. But it's all grouped into better representing these urban climates in the modeling world. That way we can simulate these and actually simulate the conditions that people on the ground are going to be experiencing, right? So can you guys see this? I don't even know where mine went. There it is. I've got too many screens. Great. Okay, I saw thumbs up. So essentially what I'm about to talk about are these parameters that are trying to represent the roughness of a surface that are then used in the modeling equations, this like linchpin modeling equation that I'm about to show you, in order to estimate the surface winds at the ground, right? Because then if you estimate these surface winds and the conditions, these are going to then set the stage for things like the fluxes and things of that nature, which are they're going to drive boundary layer processes and all these other things. So it's like, if you're not representing these parameters I'm about to show within the modeling framework to capture what's actually going on the ground, then you're kind of, it's like, you're not going to get this answer right in the first place. So let's get into it. I'm not going to show a lot of equations. The only one I'm going to show is this guy right here. And this is the equation I was just talking about. It's called the logarithmic wind profile, the log law, whatever. Essentially what this is saying is that if you want to estimate the wind speed at the ground, whatever height z above the ground, it's going to be related to this equation, where u star is just a turbulent flux, k is a constant, z is the height that you are above the ground, and then these two are parameters represented by the surface characteristics, essentially, right? You've got this d and this z naught. And again, like I said, this is critical in some form, this is lurking underneath the weather model in order to try and estimate the surface fluxes at the ground, whether it be evaporative, momentum transfer, sensible heat, the amount of like heat coming off ground, whatever. This is under there, or the wind conditions experienced by the people at the ground. If you want to get things like dispersion of chemical compositions of the ground correct, and you want to use a weather model, this is what's going to be estimating those wind conditions at the ground. So you better get this right. And if there's biases inherent in this, you're probably going to see them inside your estimates of dispersions and things like that too, at least in the weather model framework, right? So this is the creature. It's very important. And we're going to kind of look at how this is represented in an urban area, specifically this D and this Z naught, right? So what is Z naught? Z naught is essentially a characteristic length scale based on the roughness of the surface. What you can think about it in light of that equation I just showed you is essentially it is the height above the ground where the wind speed goes to 0, right? We know the winds are 0 at the ground. There's no wind blowing through the ground. So the winds are 0 at the ground, but some height above the ground, depending on how bumpy the surface is, the wind speed is also 0, right? So this is that characteristic length scale right there. Now, in order to get this in an urban area, we have to introduce another variable, this D, which basically we displace this logarithmic profile above in order to make this theory still hold. So you can see now I've got buildings on the ground. I've got to shove up my logarithmic wind profile by some distance D. And you can see my Z naught has kind of increased in distance as well because our surface is much rougher. But essentially, right, we know that this profile should be holding at least above some distance above the ground. So in the urban area, you got to think that the Z naught and the D are going to be highly related to the elements. I'm talking like trees, buildings that are actually on the ground, right? And how well are those actually represented in the numerical weather models, right? What do they look like? And you know that these urban areas are incredibly heterogeneous. You look one direction, you see a completely different array of buildings, maybe a tower sticking out of the ground, something like that. Whereas if you look a different direction completely, maybe it's completely different looking mosaic of different stuff on the ground, right? And in the numerical weather model, essentially what's happening is you have a pixel, right? You've got one pixel trying to represent that entire mosaic of roughness elements on the ground, and it gets assigned one D and one Z naught. And I would argue almost that this thing needs to change depending on how the wind is blowing and blowing over the elements and where it's coming from, et cetera, et cetera. And so we're going to try and tackle that question a little bit here. So in order to answer this question, why is it not advancing? There we go. We're going to use one approach. There's a way that you can use theory to try and back out the Z naught and the ZD. We're not going to look at that right now. Let's actually look at this other method, which is called a morphometric method. Basically, it's an empirical relationship between the geometries of the objects on the ground and what we think the Z naught and the ZD should be from these geometries. So essentially what you do is you get an idea of what is upwind. You then take how high are the buildings mean? How much deviation in the building heights are there? Things like that. You plug them into the equation and you get a Z naught and a ZD. So then we need information about the buildings on the ground, right? So what I'm showing here are two sites that we have in Indianapolis, actually. So this is part of the influx project, but right, this is very pertinent to Baltimore as well. And what I'm showing is essentially a 3-kilometer domain around our flux tower centered here. And there's a picture of our 2 flux towers. These are our communications towers. These are similar to what we're actually going to be having out in Broadway East and in Howard Park, right? So what I've done here, I'm going to go back, is I've taken high resolution LiDAR data. This is meter resolution of buildings and vegetation, and I've essentially isolated the vegetation away from the buildings too. Because you think of the drag imposed by a bluff body like a building versus a porous medium like a tree, they're going to have different amounts of drag. And these two variables that I've been talking about and harping on and on about are closely related to the drag. So they probably should be represented uniquely in order to try and determine these parameters. And there are recently been pushes to try and represent the vegetation uniquely. So it's kind of like we're trying to push towards more realism. And I'm essentially going to take this and say, okay, what if we represent vegetation uniquely? Does that make any difference? Okay, what if we don't? Does that make a difference? Et cetera, et cetera, et cetera. But I have an idea now of all the objects in the surrounding area here, which is pretty cool. So essentially now what we're going to do is I'm going to run an estimate of the upwind source area. It's called a footprint model, essentially. It's a very simplistic model for the most part. But what it's going to give me is it's going to give me an half an hour estimate for particularly measurement time, right? Because we're measuring and we're getting data from these flux towers at every half an hour. So every half an hour, I generate a footprint to estimate what the upwind area is. From this footprint, which is not perfect, this is an estimate, I can then take the geometries of the roughness objects that exist within the footprint, and I can plug them into our model and get an estimate of what ZD and Z naught are. I can do this for a whole bunch of wind directions, right? The wind direction is shifting and changing, and I'm just going to keep getting an estimate of Z naught and ZD for every half an hour. And then I can essentially pull out a mean, I can pull out deviations, all of these great things. But we're getting a change, hopefully, in Z naught and ZD based on wind direction here too, to then plug back into the model to see how well it compares to the observations that we actually are measuring on this tower, right? So you see variations in Z naught and ZD with wind direction at the end, right? So we've got the shading is actually just the range of ZD, Z naught values. So bottom, we've got Z naught, top, we've got ZD. So again, right, this is how high we have to displace the profile. This is just like a length scale represented by the objects that are on the ground. It's going to get larger. The larger the objects are, the more variability there are on the objects, et cetera, et cetera. But moral of the story is you can see variability in wind direction here. And secondly, I should mention that Kent, this thing called Kent. Oh, and I should also mention before I go into Kent, MAC is one morphometric estimate, one way to estimate it from the geometries. Cond is another way. So these are two different formulations for estimating ZD and Z naught that are typically used in the weather models too, right? So the Kent MAC or Kent Cond is where I have uniquely represented the vegetation in the modeling framework. So it's assigned a different porosity, a different drag. And you can see in like this wind direction at the one tower site, which is actually from this way where we see a lot of trees, you can see an impact from the buildings or an impact from the vegetation that differentiates these parameters. And that's cool. So it's like, okay, we see impacts from vegetation and representing vegetation uniquely. We see variability with wind direction. That's all fine and dandy and great. Now, what happens when we plug this back into this equation and we compare it to what we observe on the tower, right? Does it get the right answer? And the answer is no. Okay, ignore, there's a lot of stuff going on here. I want to draw your eyes right there, just to that panel right there. What you have is the red line going through, this is the 1-to-1. On the y-axis, I have the modeled estimate from that equation I just showed you, plugging in our lovely little parameters, and I have the observation on the x-axis. You can see there's an inherent negative bias here, and this is in U star, which is the friction velocity. This is trying to estimate the turbulent flux. On the contrary, you see a positive bias in the wind speed. So essentially what this means, and you can see here real quick, these don't really look any different. This is all the same site. And from each of these panels, all I'm changing is I'm using a different method. One of these has, so this is like MAC Kent. So this has vegetation represented uniquely. Here's MAC without the vegetation represented uniquely. Here's the other formulation Cond. Here's the Cond with the, you don't really see a difference. And this is in a site where we know, or we think that this formulation should be holding. So we're seeing that it's not doing a great job in these urban areas. Something is going awry. So what does this mean for the models? This basically means that in the modeling, this formulation is not going to estimate the wind speed. And you see this actually. There's a lot of comparison studies that have taken like surface weather obs or different observations from urban areas, and they see an inherent bias in wind speed on the ground estimated. And right, like I said before, if you don't get these right and we don't find some way to potentially correct for these biases, you're not going to get the surface conditions right. You're not going to estimate the heat fluxes and things like that quite correctly. You're going to have biases that cascade throughout the entire modeling process. And it's going to make it much more difficult to try and make on the ground decisions if you don't get like fundamental processes going on in the modeling framework correctly. I know that was a lot. That's all I got for now. I'm not really going to go into like the turbulence theory part of it. There's a whole nother turbulence stuff of like maybe why this is happening, but for the most part, it is happening and there is biases, and we're trying to answer questions on to how to better correct for these biases and maybe represent these urban systems better, enhance the model, enhance the formulations, et cetera, to try and get better representative of these urban climates in these, for these urban systems and the community people who live there. Anyway, that's all I got. Long spiel. Thanks for listening, everybody. Hopefully that wasn't too much. Stop sharing, I guess.
Questions for either Jason or Ben?
Ben, do we know what type of turf grass it is? So we did a series of surveys around Baltimore to look at the different types of cultivars, whether they're warm season or cool season. You know, they'll have very different types of phenology and physiology. So this is not specific to your site, but if we're going to extend these models over the full region, then we need to collect some additional information about the type of turf grass, management, irrigation levels, and so forth.
Yeah, I agree. This site was picked to kind of represent the low input in terms of management.
Right.
Scale. It's mowed, but that's about it.
Yeah.
If you have survey data of like what kind of species and stuff were around, that would be interesting. Yeah, I don't actually know what species it is, but it's probably tall fescue, which is a cool season turf grass, which the flux pattern I showed bears out. So, but it's also quite weedy. It's not, there's not a lot of herbicide happening either. So there's a mixture, but it's it's kind of a normal lawn.
It's interesting you say that, Larry. So we actually have quite a few turf grass sites that we've collected from outside of Baltimore and Indianapolis, and you can definitely see the signature from a warm season versus a cool season grass. Whereas like an invasive species like stilt grass in a lawn, you can see it all of a sudden just turn on as soon as it germinates and just begin to rip CO2 out of the atmosphere, almost like corn. And it's really neat. It has a completely different CO2 signature, like you were alluding to, from these cool season. You're right. In order to get these right in the modeling framework, it's very important to distinguish the two.
Yeah, let's just cross coordinate or see if the Veg and Soils team is actually looking at lawn composition.
So Ben, I've got a kind of carriage question. So when carriage is going to go to the same site, do you know how much of that field are they going to take up, remove, cover with buildings and instruments?
No, it shouldn't be any. Yeah, I don't know exactly. So I unclear about the future of this particular tower. This might be the only year for it, but there won't be any buildings out on the field. There will be instruments out on the field. So I'm hopeful that this could just still be out there, and there might be some instruments in the fetch, but it will still be a turf grass field. And
so the buildings they bring, they're going to have some portable buildings, I assume, but they're going to be off the field.
They're going to bring in shipping containers, which are going to be parked in the parking lot to the north. Yeah.
Okay. Any more questions?
So Jason, you're planning to do to basically repeat that analysis for the Baltimore area when we have the Baltimore tall towers up. Is that right?
Oh yeah, if I had the bandwidth, that'd be cool. Maybe we'll see. There's a lot of things that I'm trying to do right now. One of the things what we're kind of maybe moving forward to, I was going to get in contact with Darren and a few people, is potentially maybe doing a heat wave study of this past summer, looking at how well we can actually simulate the conditions of the heat wave at high resolution. But yeah, we'll see. We'll see what happens. I hope to do something right, because this is an important question, and it's maybe not the most interesting question, like you can't really see it happening so much, but something you need to get right for sure if you want to simulate these places.
Yeah, this is Troy Bernier here, and Jason, you did a quite thorough job there explaining that. I haven't heard it actually explained that well in quite a long time. So,
Oh, great. That's awesome
yeah,
to hear.
that was good. As for, you know, in the context of the urban environment, and the differences, why it's so important to have the right elevation inputs for your platform. So I think that's
Absolutely.
good. And if you need any help with processing that, of course, if I have the bandwidth too,
Yeah.
but if you need any help with that, any resources to tap into, if I'm available, I'll be happy to give you a hand with that.
Thank you, Troy. I appreciate that a lot. Yeah, this paper for Indianapolis, I'm hoping to have written up and out here soon. So everyone can just like look at it and repeat it. I've had multiple people say that they would like to repeat this for their sites as well, at conferences, and they're like, Jason, you need to get this out so we can kind of use your methodology and do this as well. Because yeah, it's cool. Thank you. I appreciate that, Troy.
All right, well, it looks like we're coming up right on the hour there, so I think we'll go ahead and close it out. Thanks, everybody, for the talks today.
Thank
Yeah,
you.
thanks for the
All right.
opportunity to talk as well. Appreciate it.
Thank you guys so much. Take care.